3/5 x
Negative
3/5 x plus 3 equal to 1/2 x minus 5.
this
1/2 x
minus 5.
minus 5. And you just want to solve the equation such equality.
So we are solving this? Really? Okay. Well, this is a linear equation. This is what I do with my O11 class. Okay. So we multiply both sides by 10. I would first, to be exact, I will move 3 to the other side just to make it a little bit easier to work with. Then I'll multiply both sides by 10. 3/5 multiplied by 10. And I simplify and I get negative 6x. 1/2 multiplied by 10 is 5x. And then minus 80. I will move 5x to the other side. Negative 11x equals negative 80. X is 80 over 11. There was no problem with this, right? No. I hope.
Can we go over, I know we did last time, but I'm having a hard time
Okay.
right around 3, which is 2x.
Okay.
Over, x minus 3 minus 6 over x equals 18 over x squared minus 3x.
Okay. So this is a rational equation. There are several different ways of solving it. The method, I think it's easier to explain and easier to understand, but it may not be for everyone, is this. I move this term to the other side, and I get 2x over x minus 3 minus 6 over x minus 18 divided by x times x minus 3. Then I will have to find the least common denominator a bit before I have to write two restrictions. And the restrictions are 0 and 3. And would you allow me to remind you that I have the videos posted? Okay. So please watch those. But if you still have questions, I have to work on the problem you need help with. So the least common denominator is x times x minus 3. Is that okay so far? Is that a yes? Yes? Okay. So then we have to find adjustments. There is no need for one, but I'm just making a point. 1 times this is this. X minus 3 multiplied by x gives us this, so I have to multiply the numerator by the same quantity. X minus 3 was multiplied by x, and I get this, and then the top gets multiplied by x as well. Is this okay? Are we okay so far? Okay, so then I have 2x squared minus 6x plus 18 minus 18. So 2x times x, negative 6 times x, negative 6 times negative 3, and negative 18 times 1. Is that okay?
Yeah. Well, I don't know if I just did theory. Why is the x times x minus 3
The least common denominator.
common?
Okay, very good. What do you think the least common denominator should be? It's okay.
I had no idea.
Okay, so if I want to add 1/2 to 1/3, how do I find the least common denominator? Right, because they have nothing in common, so the least common denominator must be 6. 2 was multiplied by 3. The top has to be multiplied by 3. So the fraction changes into 3 over 6. Because if I don't have the same denominator, I cannot add them. So 2 was multiplied by 2. 3 was multiplied by 2. So the top has to be multiplied by 2. So that's how I get 3 plus 2, which is 5 over 6.
Yeah, sorry, just been
That's okay. So that's exactly the same procedure. X and x minus 3 don't have anything in common, so they have to be multiplied. Also, any factor in here has to be present in the least common denominator. But since these two appear twice, I will consider one distinct, and these two appears twice, but I will consider a second distinct factor. If I had 2 here, then I would have chosen the highest power. This has 1 and this has 2, and this would have been 2. But that's not the case. Both have power 1, so both factors have to be in the least common denominator. And then the adjustments are determined the exact same way. 2 times what is 6? 3, so then the top gets a 3 as well. I cannot just multiply the bottom by 3 without multiplying the top. So actually, I condense. You can write 3 over 6 plus 2 over 6 equals 3 plus 2 over 6. So I'm skipping a step in between. So you can write 3 over 6 plus 2 over 6. But I already write it like that, so you don't have to do it twice. But that's what you're doing here. You're changing this fraction into something over 6, and you're changing this fraction into something else over 6, so you can add them. Sure. Do I have to finish this one? So once you simplify, then the numerator, the right-hand side changes into 0 over 1, and you will use cross multiplication because now this is a proportion, and you will have 2x squared minus 6x equals 0. This is 0. And at this point, some students ask me, what happened to the denominator? Nothing happened to the denominator, in case you're wondering. I crossed multiplied, and this times 0 is 0. So then I will divide both sides by 2, and I get x squared minus 3x equals 0, and I factor out an x. And that's how, from the zero product principle, I get x equals 0 and x equals 3. And it happens that the exact same thing I had to exclude because the fractions would not exist. So no solutions. Is this okay? Okay, perfect. Anything else? Other questions? Anything? Again, I'm so sorry. I'm sure that when I'm ready to go home, I'll find the quizzes. But now I can bring it up on the computer though. So what does that say?
Simplify that expression. It's going to be sorry. So 1 over x plus h parentheses squared minus.
I thought we did this together. No? No. Okay. That's fine. Very good. So this is what is called a complex rational expression. It's called more than that, and we'll talk about it over and over in this course. It's also called the difference quotient of a function, but I'll explain that when we get to it, hopefully today. I mean, obviously today. In order to simplify a complex rational expression, I have to completely simplify the top, make it into one fraction, and the denominator make it into one fraction, and then multiply by the multiplicative inverse. So I'm looking at the numerator. There is nothing I can do to the denominator other than writing it as h over 1, nothing else. So I have to find the least common denominator in the numerator, which is say it again.
X squared times x plus h squared.
Absolutely.
That's not what I got.
Absolutely, because they don't have anything in common. True. Okay, like just the previous example, what will I do next?
The numerator is
By, what am I multiplying the numerator by?
that was going to be x squared
Excellent. And what will I multiply this by?
x plus h.
Excellent. Squared. Perfect. So can anyone dictate this initial step for the numerator?
X squared minus x plus h.
Excellent. Thank you very much. Good. So now I have simplified sort of, but it's one fraction line, and the denominator is one fraction line, so I can flip the denominator. So I will write this. Copying the numerator with no change so far, but just copy the denominator. So tell me what to do with x plus h, everything squared. How much will that be? No, we have an agreement. We signed it last time.
Sorry, x squared plus 2x, xh plus h squared.
Excellent. Thank you. So x squared plus 2xh plus h squared. Perfect. Thank you. What now? Yes, indeed. Yes. Excellent. I couldn't have said it better. Thank you very much. Perfect. Good. Next step. Oh, you already said it. Okay. And now I see that the numerator, the two terms left in the numerator have a common factor. What is that common factor that I will have to pull out? Indeed. But I also like the negative too, because every time all terms have a negative leading coefficient, have a negative coefficient, I will factor out -1. And especially if the leading coefficient is negative, I will also factor out -1. What is left in parentheses? Perfect. What do you think is going to happen next? Of course. That is the whole purpose of doing this. Very good. We are going to see a lot of these in chapter 2 and chapter 3. A lot. That's why I put it in there. But we do this in pre-calc. We simplify the difference quotient, which this is for all sorts of functions. Perfect. Next question. Anything else? Anything else? Now, I strongly recommend the problems that I did not put here from the quiz. You should try them at home with Maple. Try this one. It really simplifies it nicely. I'm sorry? Oh, we did that?
Yeah.
Okay. Okay, yes, you're right. Yes. I don't think I left anything downstairs, but I'm looking for my handouts. I have a handout for you. Ah, here it is. And here, of course, here's the readiness quiz, of course. Too many folders. Too many folders. Okay. What is calculus? What is calculus? What do you think? Can anyone give us an idea? What does it consist of? Yes.
Calculating at very small intervals.
No.
It's math.
That is true. Yes. How many parts does it have? Differential and integral. What do you think the differential calculus will be all about?
Difference in distance.
Derivatives. What do you think integral calculus will be all about?
Area.
Integrals, right? Area, right. So I'm trying to see why we cannot hear.
You made it through algebra, you made it through trig, and now it is time.
Congratulations on enrolling in your first calculus class. The first question you may have is, what is calculus, and how is it different from other math classes? So to begin, the word calculus is Latin and means small stone or pebble. Calculus is the mathematical study of change. It focuses on instant rate of change and accumulation. There are two branches or two main topics of calculus. Differential calculus focuses on the study of instantaneous rates of change, while integral calculus focuses on the accumulation of areas or areas of irregular shapes. Differential calculus involves a process called differentiation or determining derivatives. The formal definition of a derivative involves something called a limit, which is where the study of calculus begins. Integral calculus involves the process of integration or determining antiderivatives or evaluating definite integrals. The definition of an integral also involves a limit.
It's all about limits.
Differentiation and integration are connected through the fundamental theorem of calculus. Essentially, differentiation and integration are opposite operations or undo each other.
That's what the fundamental
Calculus
theorem
is
of
considered to
calculus
have been developed independently in the 17th century by Isaac Newton and Gottfried Leibniz. Though there is some type of discussion as to who developed calculus first, it's generally accepted they developed it independently at the same time in the 17th century. Calculus has many applications in the field of science, engineering, and economics. Let's look at some examples to see how calculus is related to algebra and geometry, but is much more dynamic.
and the
algebra.
difference between the two.
The graph below is a function that models the distance a car is from the starting point as it drives away. Notice how we have the time in seconds along the horizontal axis and the distance in meters along the vertical axis. Analyzing the graph, notice how the distance away from the starting point increases quickly from 0 to, let's say, 3 seconds. Then after 3 seconds, the distance continues to increase, but not as fast. If we were concerned about the rate at which the car is traveling away from the starting point, we'd be concerned about the change in distance divided by the change in time. Notice how distance in meters divided by time in seconds would give us the rate in meters per second. So we know in algebra, if we select 2 points on the graph, we can sketch a line. This is called a secant line. And the slope of this secant line would give us the average rate of change, or the average rate from time equals 1 second to time equals 3 seconds. Where the average rate of change, again, is the slope of the secant line given by the change of y divided by the change of x, or in this case, the change in distance divided by the change in time. But if we wanted to know the instantaneous rate of change, or the rate at a given time, not an average rate of change, this would take calculus. Or the instantaneous rate of change at a given time would be the slope of a tangent line pictured here. So if we wanted to find the instantaneous rate of change of the car, with, let's say t equals 3 seconds, it would be given by the slope of this tangent line by evaluating the derivative of the given function at time 3 seconds. So the instantaneous rate of change is the slope of the tangent line, which would be equal to f prime of 3, which means the value of the derivative function at time 3 seconds.
That we will learn.
So using calculus, we can find instantaneous rates of change, which is much more powerful than algebra, where we can only find average rates of change. Again, looking at this secant line though, notice how as these 2 points get closer and closer together, the secant line would approach the tangent line, which brings in the idea of a limit in calculus. Now let's look at a second example. Here we have the graph of a function that models the rate a car travels for a given time, where we have the time in seconds along the horizontal axis, and we have the rate in meters per second along the vertical axis. Analyzing the graph, notice how the rate alternates from increasing to decreasing. The rate increases over this interval, then decreases over this interval, then increases, then decreases, and so on. In this case, if we were concerned about the total distance traveled by the car, since distance equals rate times time, the area under this curve and above the x-axis over a given interval of time would give us the total distance traveled. So notice how, as the time increases, the accumulation of the area under the curve decreases, and therefore the distance increases. So using geometry, we could only approximate the distance traveled by approximating the area under the curve over a given interval.
This is
So if we
chapter
wanted to
5 for us.
approximate the total distance traveled from, let's say, time equals 0 seconds to 18 seconds, we could approximate the distance traveled by approximating the area under the curve using these 3 rectangles. So using geometry, the approximate distance traveled for the first 18 seconds would be approximately the area of these 3 rectangles. If we wanted to know the exact distance traveled,
We
we
need
would have
calculus.
to use calculus, where we want to determine the exact area under the curve and above the x-axis from time equals 0 to 18 seconds, pictured here. And this area, where this area would be equal to what's called a definite integral. So again, the exact area, which represents the total distance traveled, would require calculus, and the exact distance traveled would be equal to the integral of f of x integrated from 0 to 18, which again requires calculus. Going back over to these 3 rectangles, which we could use to approximate the distance traveled, notice how if we increase the number of rectangles, approximation would get better and better. So as the number of rectangles increase, the area of the rectangles would approach the actual area under the curve, which again will bring in the idea
Of a limit.
So once again, I do want to congratulate you for enrolling in calculus, making it this far.
So we know what calculus deals with. It deals with, number 1, rate of change, which is, and we're going to talk about every aspect of it. Rate of change, which will give us a limit, actually, and which will give us instantaneous velocity, which will give us instantaneous rate of change. The second half, which is basically chapter 5, only chapter 5 for us, and beyond, in calculus 2, you'll look at applications of the integration, is all about areas and kind of going backwards to determine this time. As the professor explained, the differentiation and integration undo one another. They are inverse operations. If I differentiate an integral, I get the function. If I integrate a derivative, I get the function. In other words, they cancel their effect on x. And this is the idea of the course. You don't have to memorize any of this right now. But I want you to remember that calculus has 2 parts, differential and integral calculus. Okay, now I would like to start with our handout. And let's recall a few pieces of information that we need for our class today. So the slope y-intercept equation of a line. Slope y-intercept equation of a line. What is it? Very good, excellent, thank you. The slope of a line given 2 points. Excellent, thank you. The point slope equation of a line. Y minus y1 equals the slope, x minus x1. We don't have any difficulties with this, right? The average velocity or rate of change formula. Average rate of change. And I'm going to write it here. Average rate of change. Difference in y over difference in x. You saw in this short video the difference, the huge difference between algebra and calculus, and the huge difference between geometry and calculus. Okay. By the difference in y over the difference in x, of course, we mean rise over run. How do I determine the rise? Very good. Over x2 minus x1. However, when we talk about a function and we talk about y2, it's the same thing by writing f of x2 minus f of x1 divided by x2 minus x1. They mean the same. Okay. I would like to look at this function. I created it with Maple. I know what the function is because I knew what I wanted. And here's our first question. Describe the function assuming it represents number of bacteria, y, in thousands, function of time x in days. By looking at this function, what would you say? What would you tell somebody who has never seen a graph before? What would you say? This function does what? Right. It just tells us at any point in time what happens. But can anyone describe the trend for us? Yes.
The number of bacteria, as the days increase, the number of bacteria grows slowly, then there is a sharp increase followed by a very sharp decrease.
Right, right. So it comes to a peak. So it's increasing here quite fast, and then a little bit less, right? And then here the increase is, at this point, 0. Right? And then it decreases. Would you agree with that trend? Okay, so that's the trend. Describe the function, assume it represents number of bacteria. I would say, if you want to put it in, I will put it in myself. The function it has a sharp increase, I would say, between 2 and 8 days. Sharp increase. A peak at roughly, I would say, hard to read, I would say close to 14. And then a sharp decrease. In number, of course, in number of bacteria. So maybe they get to a certain peak and then they start dying. Okay. What is the bacteria population at x equals 8 days? How do I read that? Well, I have to draw a vertical line at x equals 8 as accurately as possible. And then I have to read the y value at that point. So what would you estimate it to be? Definitely between 4,000 and 6,000. My line is not perfect. The horizontal line is not perfect either. So you would probably say roughly about 5,000. Would you say that roughly? So approximately 5,000 bacteria after 8 days. Now I do have the exact number, of course. And the reason why I have the exact number is because, as I said, I calculated. I created the function, and then I plugged in the function 8. So that's why I know the exact value is 5,120, assuming the bacteria follows this particular function. So I will say when x equals 8, y equals 5,120 bacteria. That's their number. What is the population increment between x equals 8 days and x equals 12 days? We have not done anything with calculus yet. We're just looking at the graph. So I have to read again, I have to go back to the graph, and I have to read what happens at x equals 12. So I have to draw a vertical line. I have to read the value of y. I would say roughly 10,000. However, I do have the exact number. From the graph, I read approximately 10,000. But actually is when x equals 12, y equals 10,368 bacteria. So when I'm asked what is the population increment between x equals 8 days and x equals 12 days, what will I have to do? What will I write? 10,368 minus 5,120. And when you have that number, I'll put it in. Now, the next question is totally different. What is the rate of bacteria growth between x equals 8 days and x equals 12 days? And I need someone to help with this. How do I think about it? Do we have this number? How much?
5,248.
Very good. So between day number 8 and day number 12, the number of bacteria grew by 5,248 in number. Okay, but now here's the question. Question number 4. What is the rate of bacteria growth between x equals 8 days and x equals 12 days? How do I determine that?
Rate of change.
Exactly. Thank you. The rate of change, I would say the average rate of change between 8 and 12. How do I determine that? Exactly, perfect. Since we're talking about the average rate of change, I would say f of x2 minus f of x1 over x2 minus x1. In order not to lose track of what I'm doing, I will definitely consider this x2 and this x1, and of course this y2 and this y1, just to make sure I don't make a mistake when I plug them in. So then, my next step, I plug them in, of course, and I get 10,368 minus 5,120, 12 minus 8. I already have the number at the top because we calculated it in the previous question. So I have 5,248, and I divide that by 4. So what does this mean? And how much is it? So it's 1 and 3 and 1 and 2. No rate of change is acceptable without a measurement unit. So you can make yourself a note. Unless x and y are not specified as particular variables in the sense they're abstract, in the sense that I'm not told that y is measured in this and x is measured in that. So if the variables are abstract, then you don't have to write anything as a measurement unit. But in this case, we have number of days and we have number of bacteria, which the two variables are not abstract. variables, just plain x and plain y. So I'll say no rate of change is acceptable without the measurement unit. So 1312 doesn't mean anything. It's 1312 what?
Bacteria per day.
Excellent. Yes, since it's a ratio has to have a measurement unit that comes from the top and a measurement unit that comes from the bottom. Therefore, it's number of bacteria per day. Very good. Now, what does this really mean? One more time. It means 1312 divided by 1 bacteria per day, which means since it's positive, when we know that, we got a positive, it's a positive slope. Bacteria per day means every day the number of bacteria does what? Increases by 1,312. So that is the explanation. So coming back, in number 4, you can fill it in. It's 1,312 bacteria per day. What is the slope of the secant line between the points with x equals 8 and x equals 12? So I'm coming back to my graph. I will draw the secant line between these 2 points. This has nothing to do with the trigonometric function called secant. It's just the line that crosses the graph in 2 points. Okay, can anyone give us the slope of this line? So I'm asking, what is the slope of the secant line? Of course, 1312, indeed, bacteria per day. If you want to be considered abstract, in that case, in this particular case, I'm fine if it's just say 1312. Okay, because we're talking about a line. But otherwise, it has to have a measurement unit. Okay, very good. Now, final question. What is the rate of the bacteria growth at 8 days? We can't do that. We don't have enough tools right today to do it, to determine it exactly. We don't. We will, but today we don't. So what I can do at this point is go back to 8, draw the tangent line at that point, and estimate. Estimate the rise, find this point, estimate the rise, and estimate the run, and determine the ratio. And then I can say approximately such and such. So I draw the tangent line at the point with x equals 8 and some y value, of course. I drew the tangent line, and I determine 2 points on the tangent line. This point, of course, this point, this coordinate, and this coordinate. And then I'll estimate the rise, and I'll estimate the run, and I'll say approximately. That cannot be exact. Yes?
Why did you put that line between 2000
Because here, you're talking about between 4,000 and 6,000?
Right.
This one?
Yes, right. No, the one underneath that.
This one here?
Yes, right.
Okay. So let's suppose I have this graph, and I'm asked to find the rate of change of this function at a particular point, not between 2 points, at a particular point. I will draw the tangent line at that point, which is this. It touches the graph of the function in only 1 point. And depending on the grid I have, I will stop with the tangent line somewhere. I will find the coordinates of this point. I will find the coordinates of this point in order to find the rise over the run.
So it's
Say it again?
so that's pretty much just where you stopped at. Is not
Anywhere you want. The slope of a line is the same anywhere between any 2 points on the line. If you want to stop here and here, it doesn't matter. This rise over this run will give us the same slope, because the slope of this line is always the same. If I choose this point and this point, or I choose this point and that point, the slope will be the same. Going uphill or downhill, it doesn't matter. The slope of the hill will stay the same. So you stop anywhere you want. Good. So what have we learned so far in this particular example? We know what the average rate of change of a function between 2 points is. We know that we don't have enough tools to determine the rate of change at a particular point. So for example, if I drive my car to New York, let's say, and you call me and you say, tell me what your odometer says right this second, I will read to you 59. That's the instantaneous velocity. Well, I can determine for this, the bacteria, when they grow, they don't have an odometer. So I can look and say, what is the rate of change at this particular instant? I can determine the rate of change between 2 points. I can tell you I left home at 4 o'clock and I got to New York at 10 p.m. and I can determine an average rate of change between those 2 points. I can determine the average rate of change between 8 p.m. and 10 p.m. as well. But if you ask me, what is your rate of change at a particular instant? If I don't have an odometer, I won't be able to tell you. But if you give me the function, the distance function, I will be able to determine algebraically, with calculus I should say, I will be able to determine the instantaneous rate of change at any point on my way from home to New York. Coming back here, I did determine the slope of that line. I cannot show you just yet how I did it because we are not there yet, but I did determine it. And in my next step, I showed you the function that I used to create the initial graph. That is the function that I used, polynomial function, negative x to the fourth plus 18x cubed. I determined the slope. Again, I cannot tell you just yet how. And the slope was 1408 bacteria per day in that particular day, on the 8th day. And with that slope, I determined, and I used one of the points, and I'm going to do that together with you right now. I determined the slope of the tangent line, and also I determined the equation of the line. And what I did next, I plotted both. So this is the function, which is this. This is, I'm going to show you how I determine, not this just yet. In the next class, I will show you that. So I determined the equation of the tangent line, and then I graphed them together on the same, using this syntax, this command. These are braces. Careful how you put it in if you want to. So what I got was, I showed that at this point, the line is tangent to the graph of f of x. And this is the rate of change, the instantaneous rate of change of the bacteria on that day. Having the slope, we will determine the equation of the line right now. Here's what I did next. I zoomed in somewhere between these 2 points. You cannot even see them or tell them apart, because somewhere here and zooming in, they are overlapping. Okay, so it's clear that that is the slope. That is the slope, and that is the equation of the line that is tangent to the graph at 8 comma, what I gave you before, what was it? 8 comma 5,120. And here's how we determine having the slope, right? We just reviewed that, having the slope 1408 bacteria per day. And the point, I want to practice this with you because we're going to use it a lot. 85120. How do I determine the equation of the line? 1 minute. Let's do it.